Axially loaded members. Okay, so with axially loaded members, this is to calculate and investigate different stresses as well as forces that are in different sort of sections within specific materials. And you get essentially a series scenario and a parallel scenario, and we'll be looking at both of them. So let's first look at the series scenario. Okay, so if you have to take this piece of material into consideration, okay, so if I had on this plate some force, this plate is not able to move backwards, it's stuck over there, and I had to apply some force, pulling force over there, and have some pulling force over here on the right hand side. The force applied onto this specific object, it's going to be the same whether it is through this thick piece over here or this bolt piece over here, whether it's through the head part over there or that welding joint over there, or whether it's through that thin or thinner piece over there. The force is going to be the same right through. But remember, force is equal, or stress is equal to force over area. Okay, so the area is larger over here, the area is even larger over there, but the area is thinner over there. So the thinner this and smaller the area is, the larger the stasis is going to be. So yes, the stasis over here is going to be more than the stress over here, and the stress over here is going to be less than the stress over here. Okay, so you can consider it very much in a similar way. If you were, for example, if you were hanging from your finger, so you might have your finger that's coming up over here, and that is hooking over some bar over there, and then obviously it comes through to your hand, which then comes through from there to your arm, and then from your arm you're just hanging from one hand or one arm though, that goes in through to your body. Let me move this up over here, and then from your body it goes into your legs. Eventually this is like a side view of your profile sort of that you would be seeing. And yet here on your feet you had a big weight that was placed over there. The force is going to be of this weight acting down on it is going to be causing the same force to be going through the legs over here. It's the same force going through your body over there. It's the same force going through your arm over there. It's the same force going through your finger over there. But obviously, hanging from your finger, you're going to feel it in your finger. Your finger is going to be aching because there's going to be a lot of stress over there. The area is very thin over there. It might not be as stressful and as aching in your arm because there's larger cross-sectional area over there. Your body might not feel the intensity of this force acting on it because it's much larger. But coming down, you might find that your feet or your legs will start aching because it's a thinner cross-sectional area. So the same type of principle happens. So remember, stress is equal to force over area, okay, and as area decreases means that the stress increases, but the force will always be constant. That's in a straight, linear and series type of configuration. Okay, so there's a few equations that we need to look at, which are going to be important ones that you're going to be looking at. The first is the sum of forces is equal to 0. We know for equilibrium systems, the sum of forces must always be equal to 0. If you've got in a series of members change in length due to the forces acting on it, then the total length change in length will be equal to the sum of the differences of the change in length of the different sections. So section AB, if that changes by a certain length, you're going to add it to section BC with the change in length of that piece plus the change in length of section CD. And then you've all seen this equation before. The change in length is equal to stress times the original length divided by E. Okay, and that's also equal to F, the force, multiplied by the length, divided by AE, A being your cross-sectional area. So those equations are important ones that we will be looking at, and that will fit into most of the solutions that we are going to be at least looking at. Okay, so the best way to do this is to use an example. Okay, so if we look at this specific example, we've got a piece of round bar over here. We're told that it is 20 millimeters in diameter. That's fastened to a thicker round bar over here, which has got a cross-sectional or a diameter of 30 millimeters, and then that's attached to a thinner bar over here, which has got a diameter of 25 millimeters. And we've labeled over here A, B, C, D, and E for the different sections of it. We see over here that there's 20 kilonewtons acting in the right hand direction. There's also 40 kilonewtons acting in the right hand side direction over there. Okay, we've got 30 kilonewtons acting here at point C, and then we've got a force F acting at point E. Okay, so the first thing that you might be asked is determine the magnitude of force F for equilibrium members AE. Okay, so find F. Okay, and for us to do this, we're going to be using the equation that we've looked at, which is the sum of forces is equal to 0. Okay, and whenever we do these type of calculations, we're going to be using a uniformity in terms of if the force is acting towards the right hand side, then that will be a positive value. When it's acting towards the left hand side, it will be a negative value. Okay, so therefore we've got our 20 kilonewtons over there, so that's 20. We've got 40 going towards the left, so that's minus 40 over there. Let's go through. We see there's 30 kilonewtons going to the right, so plus 30. And then we've got a negative F force towards the left, or minus F over there, and that is equal to 0. Okay, so now we make F the subject of the formula, so we bring F across to the other side, and that will mean it's 20 minus 40 plus 30, which is equal to 10 kilonewtons. Okay, so therefore F is equal to 10 kilonewtons. Okay, now that we've done that, the next thing that you might be asked is determine the total change in length. Okay, so find total delta L. And you're told that E is equal to 200 gigapascal. Right. Okay, so now to do this, remember that the change in length of total is going to be equal to, so if we look over here, that's going to be the change in length of AB plus the change in length of BC plus the change in length of CD plus the change in length of DE. Okay, so this is the one equation that we will be considering. Also remember, as I mentioned before, delta L is equal to stress times L over E, and that's also equal to F L over AE. And we get that because stress is equal to force over area. Okay, so that's what we're going to be using over here. Okay, so now that we've done that, I'm going to leave this in this fashion so that we can at least see the picture over there, and I'll place a new sheet of paper over here to do the calculations. Okay, so first let's look at AB. So the sum of forces is equal to 0. Okay, so therefore the force of AB is going to be equal to, or at least the force of AB, okay, is plus 20 over here. Okay, but now something that you need to take into account, if we're looking at member AB over there, a similar approach we have to do as we did with the beams, in terms of use a piece of paper to cover up the rest. Okay, so in this scenario we're only looking at AB. Okay, and so AB plus is 20 over here. Remember, to the right hand side is positive, so plus 20. Okay, and that's equal to 0. Now you might ask yourself, why aren't we using saying, well, minus 40 over there? Well, this 40 kilonewtons is at B. Okay, and we are covering up at B. We're not looking at anything that's at that specific point, only to the left of it. Okay, so that's important to take into account. Okay, so if we do that, therefore the force AB is equal to minus 20 kilonewtons. Okay, and now this negative sign tells us now something new. So we are going to, whenever we see a negative sign over there, it's going to imply that it is compression. Okay, so we've got two type of scenarios that we can have. We can have tensile, where it's a pushing or a pulling force, and we can have compression, where it's a pushing force. Okay, so over here, because you've got this force acting that's on AB, it's going to squash onto that specific member and it's going to cause compression. Okay, so if it's negative, we consider it as compression. The area, the cross-sectional area of AB. Okay, so remember that's pi d squared over 4. Okay, so that's equal to pi times the cross-sectional area over this, 20 millimeters. Okay, so that is times 0.02 meters squared over 4. Okay, when we do that calculation, that's equal to 314.16 times 10 to the minus 6 square meters. Okay, now that we've done that, we can use our change in length equation. Okay, so change in length for AB is equal to, okay, so remember we said change in length, so delta L is equal to FL over AE. Okay, so we're going to be using that equation. Alright, so the force that we've got is negative 20. Okay, so that is minus 20 times 10 to the 3, because it's kilonewtons. Okay, we're going to multiply that by the length. If you look at this over here, okay, I haven't told you what length this is. So this over here is 0.5 meters. From B to C is 1 meter. So from there to there is 1 meter. From C to D is 0.5 meters. And from D to E is also again 0.5 meters. Okay. So the change in length is equal to this minus 20 kilonewtons over there. Multiply that by 0.5 meters. Okay. And then we're going to divide that by AE. So A we've found out to be 314.16 times 10 to the minus 6 square meters. And we're going to multiply that by the 200 gigapascal, which is 200 multiplied by 10 to the 9. Okay. Do this calculation and we get an answer of negative 159.15 times 10 to the minus 6 meters. That's going to be the change in length. Now, because it's negative, it's telling us that there's some compression happening. Okay, so that's the reason we get that specific answer. Okay. Now the same approach we're going to be doing, but this time we're going to be doing it for BC. Okay, so we've finished around with AB. Now we're going to do BC. Okay, now when it comes to BC, again I'm covering up from C all the way across to the right, so we're only going to be looking towards the left. Okay, so for BC. Okay, so sum of forces is equal to 0. Therefore, the force of BC is equal to, or the sum of force of BC. Okay, and then we've got plus 20 over there, which is the at A. We've got minus 40 because it's going towards the left. Okay, and that is all. We don't see any other forces over there. That's equal to 0. Okay, so now make FBC the subject of the formula. So therefore, FBC is equal to minus 20 plus 40, and that's equal to 20 kilonewtons. It's a positive value, so therefore it means it is tensile. Right. The area of BC, cross-sectional area of BC. Let's calculate that. Okay, so area is equal to pi d squared over 4. So we've got pi. D is 30 millimeters over there. So that is multiplied by 0.03. That's all squared. Divide by 4. Okay. And we calculate that and we get 706.86 times 10 to the minus 6 square meters. Okay, now that we've calculated that, we are able to then say, well, what is the change in length of BC? So delta R of BC, okay, that is equal to, remember we've got force. So the force we've calculated was 20 kilonewtons. So that is 20 times 10 to the 3. Okay, multiplied by the original length. Well, that is 1 meter. So multiplied by 1. And then we're going to divide that by the area. Okay, so the area of BC we've calculated. Okay, so that is 706.86 times 10 to the minus 6. Multiplied by E, and E we are told is 200 gigapascals, so that's 200 times 10 to the 9. Alright, and then we get a final answer of 141.47 times 10 to the minus 6 meters. Okay. Now I'm going to underline these just so it's easier for me to then identify and track it later on. Right, so now that we've done that, let's have a look at our next section, which will be CD. Okay, so with CD, I'm covering up from D towards the right, and we're looking at everything on the left of it. Okay, so for CD, sum of forces is equal to 0. Okay, so therefore the force of CD plus 20 over there minus 40 over there plus 30 over at C is equal to 0. Okay, so therefore the force of CD is equal to minus 20 plus 40 minus 30, and that's equal to negative 10 kilonewtons. Okay, so that tells us that it is compressive. Okay, now keep in mind the cross-sectional of BC, which is 30 millimeters for the diameter, is the same for CD. So we've already calculated it, so we don't need to calculate it again. Okay, so the area of CD is equal to the area of BC. Okay, so therefore the change in length of CD is equal to, so we're looking at, again, that formula that we looked at of delta L is equal to FL over AE. Okay, so we've got a force that we calculated, that's negative 10 kilonewtons, or to the power of 3. Okay, multiply that by 0.5, because it's 0.5 meters in length, and we divide that by the area, which we've calculated to be 706.86 times 10 to the minus 6 square meters, and that's multiplied by 200 gigapascal, and that's for E. Okay, so this E value is something that you'll be given as the properties of that specific material. Okay, so now that we've done that, we get an answer of negative 35.36 times 10 to the minus 6 meters. Alright, let's have a look at DE. Okay, so now place a piece of paper over there over E. Okay, so remember now the sum of forces is equal to 0. Okay, so therefore the force of DE plus the 20 kilonewtons over there, okay, minus the 40 over there, plus the 30 over there, that's equal to 0. Keep in mind we're not taking into account this F value over here, because that's covered by the piece of paper. Okay, a big mistake that is often made. Okay, so therefore the force of DE is equal to minus 20 plus 40 minus 30, and that is equal to negative 10 kilonewtons. Okay, and that tells us it is compressive. Right, the cross-sectional area of DE. Okay, so again, pi d squared over 4, so that's pi multiplied by d. D is 25 millimeters, so that's 0.025 squared over 4. And that's equal to 490.87 times 10 to the minus 6 square meters. Okay, now that we've done that, let's have a look at the delta L. So again, delta L of DE, and again we're going to be using this formula over here. Okay, so the force is equal to negative 10, so minus 10 times 10 to the 3. The length of that piece is 0.5 meters, so multiply by 0.5 meters. Divide that by the area, which we've calculated to be 490.87 times 10 to the minus 6. Okay, so that is 490.87 times 10 to the minus 6, and multiply that by 200 gigapascal, so that's 200 times 10 to the 9. Okay, and so when we calculate this, we get the answer of negative 50.93 times 10 to the minus 6 meters. Okay, now that we've calculated all of these changing lengths, we're going to come back to our equation over here, which is the change in length of total is equal to the sum of the change in lengths that we've looked at over there. Okay, so for us to do that, we're going to be able to do that. So we're going to say therefore delta L total is equal to, so the delta L of AB was equal to minus 159.15 times 10 to the minus 6. Okay, the delta L of BC was 141.6 5.47 times 10 to the minus 6. The length of CD was minus 35.36 times 10 to the minus 6. The change in length for DE was minus 50.93 times 10 to the minus 6. And adding it all up together, we get an answer of negative 103.97 meters. Okay, so essentially we can say that it decreases by 104 millimeters. Okay, so keep in mind this is times 10 to the minus 6. I got the units over there. So it decreases by 104 millimeters. Well, correction over here. So it's actually times 10 to the minus 6. So it decreases by 104 micrometers, not millimeters. Okay, so just be careful of the units over there. It's micrometers. Okay, let me scratch it out and write it rather micrometers as such. Okay, so it's quite a small amount that it decreases by. And for micrometers, it's not, probably won't be, well, it's not going to be visible by the eye, but it can be quite substantial when you've got a very size-fitting scenario of your different materials. Okay, so that is the chain, at least a series examples for at least these specific members, or the axially loaded members. And so these are sort of the very similar type of principles is going to be taken into account. So always remember, whenever you've got a series type of scenario, take into account that you're going to have to look at it. You're going to have to look at the cross-sectional areas of each individual section. And then once you've done that, you're able to calculate the change in length for, well, before you do that, just calculate the sum of the forces to make sure that's equal to 0. So place your piece of paper over up to the member that you are looking at. So it's going to be AB, for example, or BC. And don't take into account the force at that specific point where you are going to be considering. So if you're looking at force BC, we're not taking into account the 30 kilonewtons over there because it's covered by the sheet of paper. Okay, so look at the forces, sum of forces, make that equal to 0. Once you've done that, then we're going to be using our equation over here, where the change in length is equal to the force multiplied by length over AE. Okay, and then once we've got the change in length calculated over there, we can add all those change in lengths together to obtain our final length, or at least a final change in length. We had a look at the series scenario, so let's have a look at the parallel type of scenario. So what I've got over here is a bolt. I'm placing a washer onto it, and then I'm going to be placing it inside this copper tube, and then I'm going to place another nut on the end of it, and I'm going to then place this I place a washer on the end of that, and then I place this nut over here, and I start tightening this nut. And as I'm tightening it, what's going to happen? Well, there's going to be compression on this copper tube because I'm tightening it. But as I'm tightening it, that also means that there's going to be some tensile forces acting on the bolt itself. It's going to be, because it's basically now pulling away from each other, while it's actually also causing this copper piece of material to have compression on it. Okay, so in this scenario, with the bolt being in the center of it, that will have some tensile forces acting on it, yet there will be compression forces on the copper material. And this is a parallel scenario where you've got a composite material being of different types of materials, and it has been subject to different forces or compression and tensile. Okay, so keeping that in mind, let's just have a look at some formulas that's going to be important to know and that you'll be using. Okay, so firstly, the sum of the forces is equal to the load force. Okay, so the force acting on the bolt and the force acting on the copper tube, add them together and you'll have a total force of the load that's on it. Also keep in mind that the change in length of the one material is equal to the change in length of the other material, which is equal to the change in length of the third material. So if this copper material is going to be compressed by a certain amount, it's also going to mean that the steel bolt is going through it will also have to change in length. And you've got to keep in mind that the amount that this bolt is going to be expanding will be the same amount as what the copper piece is compressing. Okay, so they are always then equal. Right, so then we can consider the tube, the forces on the tube to be equal to the forces on the bolt. In this equation that we will be using as well. And then the compression of the tube plus the elongation of the bolt is equal to the actual moment of the nut. So in other words, if we add a change in length of the tube and we add it with the change in length of the bolt, that's going to be equal to the number of turns of that nut. Okay, so this nut, in terms of the amount of times we're able to turn it, and it's also going to be, that's going to be multiplied by the pitch. Okay, so if you have a look at this specific bolt, it's got a certain pitch over there, and if it had a finer pitch, you would have to turn the nut a lot more. If it had a more rougher pitch, you would have to turn the nut much less. Okay, so it is a situation where that pitch then also has an influence in it. Okay, so now that we've had a look at that, let's have a look at an example. Okay, so we're going to consider a round steel bar that is 25 millimeters in diameter. So as you can see in this diagram, it's there in the center. Very much the same scenario we've just looked at in terms of the copper pipe inside with the steel bolt. And it is 300 millimeters long. Okay, so we know that the length of this is 300 millimeters long, and it's placed inside a tube of the same length. Okay, and it's a copper tube. Alright, so the inside diameter is 30 millimeters and the outside diameter is 45 millimeters. That's of this tube itself. Rigid plates are placed on either end, subject to a compressive load of 75 newtons. So these rigid plates, they're not doing anything, they're just distributing the load to make sure that the same load is over the on the copper pipe as well as on the steel bar in the center. We're told that the E of steel is equal to 200 gigapascal and the E of copper is 100 gigapascal. Okay. Determine the stress in both materials. Okay, so we're going to be having a look at that. Now, before we start doing any calculations, we've got to look at the area. Okay, so we're going to be looking at the area of steel. Okay, remember pi d squared over 4. Okay, so it's pi times d squared over 4. Okay, and that's equal to pi multiplied by, so the diameter of the steel, we are told that that is 25 millimeters. Okay, so that is equal to 0.025 meters, we always work in meters, squared divided by 4. And that gives us an answer of 490.873 times 10 to the minus 6 square meters. Okay, you'll notice that I always have about 3 decimal places. 3 decimal places gives you a relatively accurate result, rounding to 3 decimal places. You often have that some people go and write 8 numbers after the decimal point. It's not always that needed, so it makes it easier just to keep it to 3 decimal places. Okay, let's look at the cross-sectional area of the copper. Okay, so again, pi d squared over 4, so that's pi over 4 multiplied by, now keep in mind, it's a tube. Okay, so we need to basically say what's the outside diameter minus the inside diameter. Okay, so we're looking at the outside diameter, which we are told is 45 millimeters. So therefore it's 0.045, that's all squared. And we minus from that the 30 millimeters, which is the inner diameter. So that is 0.030 squared. And we get an answer of 883.573 times 10 to the minus 6 square meters. Okay, so now that we've done an area calculation or cross-sectional area calculations, we can go to the next step. So the next thing we're going to be looking at is, as we've looked at the formulas, is that the change in length of the steel is equal to the change in length of the copper. Okay, so that's the first equation we need to keep in mind. We also have to keep in mind that the sum of the forces equals to the load force. Okay, so we know that the force of the steel is equal to the, or at least that plus the force of the copper is equal to 75 times 10 to the 3 kilonewtons. Okay, or some 10 to the 3 newtons. We don't need to have the kilonewtons over there because we've already multiplied by 10 to the power of 3 for the kilo. Okay, so that's that compressive load of 75 kilonewtons that we've been given. Okay, so that's going to be our second equation we're going to be keeping in mind. Okay, so if we look at equation 1, remember the equation of change in length is equal to stress times original length multiplied by E. Okay, so with that we are able to place that into our equation 1. Okay, so from 1 we can say, okay, so the change in length of steel would be equal to, using this formula over here, that's the stress multiplied by the length over E. But that is all for steel. And we say that that is equal to, and change in length of copper is equal to, if we use the same formula over there, that will be stress multiplied by length divided by E of copper. Okay. Now the thing is though, is we know that the length of steel is equal to the length of copper. At least that's what we are given. We're told that they are both of equal length. So the length of the copper is the same length as steel. So therefore we can actually go and say, well, we can cross out these L values over here because they're equal. Okay, so therefore the stress of steel over and E for steel, we're told that's 200 gigapascal, so that's 200 times 10 to the 9 is equal to the stress of copper divided by, and E for copper is equal to 100 gigapascal. So 100 times 10 to the 9. Okay, so now if we look at this, we're able to cancel out this times 10 to the 9 over there, and we can calculate that therefore the stress of steel is equal to 2 times the stress of copper. Okay, so that we're going to keep in mind that answer over there. Right, so now that we've done that, let's have a look at at our other equations that we looked at. Okay, so we did say that the force of steel plus the force of copper is equal to the 75 kilonewtons. Okay, so force of steel plus the force of copper is equal to 75 times 10 to the 3 newtons. And if you remember, that was our equation 2. Okay, so now let's look at that. Remember, stress is equal to force over area. Okay, so we're going to be using that same equation. So if we want to find out force, force is equal to stress multiplied by area. Okay, so therefore we can say that the stress of steel multiplied by the area of steel plus the stress of copper multiplied by the area of copper is equal to 75 times 10 to the 3 newtons. Okay, so now what we're going to do is we're going to substitute values into this, but we've just calculated over here that the stress of steel is equal to 2 times the stress of copper. So wherever we see stress of steel, we're going to substitute 2 times the stress of copper. Okay, so therefore we're going to say that 2 times the stress of copper multiplied by the area of steel. The cross-sectional area of steel we've calculated. Remember, that was 430.873 times 10 to the minus 6 square meters. Okay, so that's going to be 419.873 times 10 to the minus 6 plus the stress of copper multiplied by, and we're looking at the cross-sectional area of copper. And if you remember, we did the calculation of that, and that was 883.573 times 10 to the minus 6 square meters. Okay, so that is 883.573 times 10 to the minus 6 square meters, and that is equal to 75 kilonewtons. Okay, so now we've got one variable over here that's unknown, the stress of copper. So we're going to make that the subject of a formula, and you calculate that, and you find that the stress of copper is equal to 40.207 megapascal. But keep in mind that the stress of steel is equal to 2 times the stress of copper. Okay, so therefore the stress of steel is equal to 2 times of that. Okay, and that's equal to 80.414 megapascal. Okay, now that we've done that, the next thing we're going to be looking at, what is the total change? Or total change in length. Okay, so we're looking at the total change of this complete composite system that we're looking at, that we've got. That's the copper and the steel. Okay, so remember that we said, well, the outer length of the total change in length is equal to the change in length of the steel. Okay, because the change in length of the copper is going to be equal to the change in length of the steel. Okay, so we've got that equation that we are able to use, that all the change in lengths are going to be equal. Okay, so with that, we're going to say that's equal to the stress multiplied by the original length over E, and we are going to be looking at only the steel at the moment. Okay, so that's equal to the stress we've just calculated for steel is 80.414 megapascal. Okay, so that is 80.414 times 10 to the 6 multiplied by the length. We were told it's 30 millimeters, or we were told it is 300 millimeters in length, right? Okay, so that is multiplied by 0.3 meters, and then we divide that by the E of steel, which we were told is 200 gigapascal, or 200 times 10 to the 9. Okay, so we do that calculation and we get an answer of 120.621 times 10 to the minus 6 meters. Okay, so we can say the bar is compressed (0.121 micrometers). Okay, so times 10 to the minus 6 would be micro. And we told us that this composite material was compressed. So we know it is compressed by those forces, so therefore we know it is compressed. Okay, so again, just keep in mind it's a similar type of procedures will be sort of used, but these are the important equations to keep in mind. A little bit different to the series type of scenario, but over here we've got, in the parallel scenario, we've got a sum of forces equal to the load of, at least the load force. Okay, a change in length of the one material is equal to the change in length of the other material. The forces of the tube would be equal to the forces of the bolt. And then we've also got a situation where the change in length of the tube plus the change in length of the bolt is the number of turns of the nut times the pitch. Okay, so let's have a look at an example where we've got this scenario as we've looked at. We've got the copper tube that's in the bolt. Again, so even though the dimensions might be a little bit different, the same scenario applies. Okay, so we've got a steel bolt. It's 15 millimeters in diameter, and that's inside a copper tube, which has got an inside diameter of 26 millimeters and an outside diameter of 32 millimeters. The length of this composite material is 200 millimeters. The screw thread pitch is 2 millimeters. Okay, the nut is tightened by 1/8 of a turn, and we are told the E value of steel and the E value of copper. Okay, so how would we go about to calculate this? Okay, so we know that the force of the tube is equal to the force of the bolt. And remember, we've got the equation that stress is equal to force over area. So we're using that same equation. So therefore, the stress of the tube multiplied by the area of the tube is equal to the stress of the bolt multiplied by the area of the bolt. Okay, so we manipulate that formula a little bit, and therefore we can say that therefore the stress of the tube is equal to the area of the bolt over the area of the tube multiplied by the stress of the bolt. Okay, so let's have a look at what that will equal to. So remember, area is equal to pi d squared over 4. Okay, so that's equal to pi. The bolt, we are told, has got a diameter of 15 millimeters. Okay, so that's multiplied by 0.015 squared, and that's all over 4. Then we divide by the area of the tube. Okay, so again, we've got pi times d squared. Remember, now it's inner and outer diameter we've got to keep into account, so that is outer diameter, which is 0.032 squared minus 0.026 squared. Okay, and then that is all over 4, so we can multiply it by 4 on the top. Right, and that is multiplied by the stress of the bolt. Okay, so we do this calculation. As a matter of fact, the pi's will be able to cancel out with each other, the 4's will be able to cancel out with each other to simplify the equation a bit, and that would be equal to 0.646 multiplied by the stress of the bolt. Okay, now let's have a look at another equation that we have been mentioning. The stress of the tube, or the sorry, the change in length of the tube plus the change in length of the bolt is equal to number of turns multiplied by pitch. Okay, so remember, change in length is equal to stress times length over E. Okay, so we can use that same equation. So therefore, stress times length over E, all for the tube, plus the stress times length over E, all for the bolt, is equal to an eighth, because the number of turns we did was 1/8, so 1/8, and multiply by pitch, and pitch we were told is 2 millimeters, so that is 0.002 meters. Okay, so therefore, now we know that the stress of the tube, we just calculated that, is equal to 0.646 stress of the bolt. Okay, so we're going to use that, 0.646 stress of the bolt. Okay, multiply that by the length. We were told that it's 200 millimeters, so multiply by 0.2, divide by, and then we got the E value for the tube, and E value in the tube is made out of copper, so that's 100 gigapascal. So let's divide by 100 times 10 to the 9 plus. Okay, so now we've got the stress of the bolt. Okay, so we don't know what that is. We're busy calculating it. So that's the stress of the bolt multiplied by the length. The length we are told was also 200 millimeters, so that's multiplied by 0.2. And we have the E of the bolt. And the bolt is made out of steel. Okay, so that's 200 times 10 to the 9. And then if we have to say 0.002 divided by 8, that will equal to 0.00025. Okay, now that we've done that, we've got one unknown, the stress of the bolt. Okay, so we can calculate what the stress of the bolt is. So therefore the stress of the bolt is equal to 109.03 megapascal. Okay, but now what we've got to keep in mind though is this compression or tensile? Well, we know it's tensile. Okay, we also calculated that the stress of the tube is equal to 0.646 of stress of the bolt. Okay, so we know what the stress of the bolt is, so therefore put into that formula, so therefore the stress of the tube is equal to 70.49 megapascal. Okay, and then again we've got to take into account that this is now a compressive stress. Okay, so as you can see in this specific example, we actually went and used the equation where the sum of the change in length is equal to the number of turns multiplied by the pitch. And so I think with most of these type of problems, the best thing is to write down all the information you have. Like we've got over here in the beginning, write all the information over there. Write out all the equations that you know that will be used for that specific or for this specific section. See which ones are unknown, see how you can correlate them together, because sometimes you might have to use two formulas to be able to find two unknowns, and then from there you're able to calculate what the final value is.